Hello, this is video 41. And even though those pictures are cool and easy to look at when we're trying to figure out the definition of some basic terms, at some point if we're going to use them, we got to think about how on earth we're going to be represented in code. So let's talk about graph representations. Graph representations as data structures. Roman numeral number 1, that looks official, doesn't it? Adjacency matrix, A-D-J-A-C-E-N-C-Y matrix, M-A-T-R-I-X. A two-dimensional array, like you used in the haystack. For G1, these are examples, by the way. It's not a general picture necessarily. I'm going to have to get a better marker. I hope I have a better marker. Please, may I have a better marker? Let me see if brown works better. Sorry about that. Across the top, I put the names of all the nodes, and not necessarily in any particular order, but I'm going to make it, yeah, that works better. Amazon, and then eBay, and then Facebook, and then Google, Transylvania, Twitter, and Wikipedia. Twit, Wikipedia. There. Now, not only, and those are alphabetical order, it looks like, by the way, I also need to label the rows that way. And these could be, of course, these could be rows and column numbers, where somewhere maybe an array, this is element 0, that's element 1, and so on down the line. You get the idea. So this is the first stab at how we might want to represent this in code. Amazon, eBay, Facebook, Google, Transylvania, Twitter, Wikipedia. Now, you don't have to do this, especially if you're using line paper, but I'm going to draw faint lines across here just to try to keep my rows straight as much as possible, and maybe even some columns here. There, that'll hold everything in place, maybe. An adjacency matrix for, let's see, this G1 must have been, looking at my notes here, that must have been undirected and also unweighted. It was on everything. And you can mix and match those. You can have undirected but weighted and directed but unweighted. So there are actually 4 different combinations of those descriptions of graphs. This one is going to be dull. I could either use 0 or 1 to say yes or no whether or not there's an arc connecting them, or I could use true, false for Boolean values. I'm going to assume the entire matrix is nothing but false, but Amazon is directly connected, also known as adjacent, to Facebook, Google, and Transylvania. Is that right? Was Amazon connected to Transylvania? That doesn't sound right. It is. Amazon is connected to Facebook, Google, and Transylvania. I should trust my slightly younger self that filled this out to be correct. eBay is only connected to Google. I'll go back and double check these after I've got them up here. Then Facebook is adjacent to Amazon and Google. See where I'm putting the trues? Everything else is false. True means there does exist a single arc between the two. Google is adjacent to Amazon, eBay, and Facebook, like so. Transylvania, only Amazon, no, Amazon, Twitter, and Wikipedia. And Twitter is adjacent to Transylvania and also Wikipedia. You can double check these. You have that picture of the graph right in front of you in your notes. Wikipedia is adjacent to Facebook and Transylvania and Twitter. Now, that's not a terribly good parity check here, but for this undirected, I'll put that back over here as a review. Undirected, unweighted graph. Either the arc is present or it's not. So all we need is a Boolean value, true or false, to say whether or not that arc is present. Another thing to notice, if I drew a dotted line here, this matrix is what we in the biz would call symmetric. In other words, if, let's call this the G1 matrix. G1 row column entry will always be equal to G1 column row entry. So I'll choose this one. Google is adjacent to eBay. Well, then eBay has to be adjacent to Google. See how that works? So if you draw a line and fold this in half, then all those T's are going to match up with each other. Why is that important? Well, it may be important, it might not be. Because of this, we actually have all information about this graph represented twice in this two-dimensional matrix, and we can get away with just half of that. We don't need to take up all this much space. Normally, though, for applications using graphs where the choice, the better way to represent the graph is the adjacency matrix, we go ahead and keep the whole thing anyway. I mean, we are probably going to need a two-dimensional array anyway, and we might as well use the whole thing. It actually makes lookups faster. If you wanted to know if there is a connection between eBay and Google, you can go to the eBay Google, or you could go to the Google eBay. It's just a lot faster to do lookups and implement your algorithm that way. Okay. I don't know what else to say about that one, except you are now in the way, that one. Let's try it for G2. I'm going to keep my matrix since that's so carefully drawn. Oh, I guess I can't, can I? All those T's in there are in the way. Okay, now we go. Not G1, this is G2. Still adjacency matrix. And for this one, I'm just going to use the first letter of the places where we were, the Art Center, BSc and everything. Art Center, BSc, then C, D, E, F. Well, cool how that worked out, huh? That's the first letter of each of the node names in graph G2. Same thing, rows and columns, A, B, C, D, E, F. And we still represent connections. Those arcs, the arcs are the entries inside the matrix, matrix itself. I'm going to stop even trying on that. Now, if you look back at your carefully drawn illustration of graph G2, if I recall, we could go from A to B in 20 minutes, is that right? So we'd put a 20 here rather than true false. In other words, we've got more information about each arc we're going to have to represent in this weighted, directed graph. Because it's weighted, we can't get away with Boolean values or zeros and ones. We need to put some representation of the weight. Now, I put a 20. That's a tiny little integer. If it's airlines or whatever, I mean, these could be non-trivial data values in their own right. So we could have a two-dimensional matrix here of some pretty good-sized value types for our matrix. From A, I can go to D with a weight of 10. From B, I can go to C, if I've written this down correctly, with 15. From B, I can go to D with 15. C, I can go to B with 7. Double check me, look at graph G2. D can go to C with 2. It can go to E with 5. And can go to F with 10. E can only go to C with 8. And F can only go to C with 1. That, I don't know, that just doesn't sound right, does it? Let me take a quick look if I can find my notes from a previous video life. F can only go to Cowgill, yeah, with 1. E, entrance on Broadway, can only go, yeah, okay. I'll assume the rest of it's correct. Now, since it's weighted, we've got numbers rather than Booleans. Since it's directed, it is not symmetric. So there is an arc from A to B, yes, but there is not one from B to A. So I can't go back and forth that way. There you have it. Two different adjacency matrices where one of them is directed, weighted, and the other one is undirected, unweighted. And there are two other possibilities for orientation of the graph. This is Roman numeral 1 of major way to represent graph. In the next video, something to look forward to, we'll look at major way to represent it, Roman numeral 2, which is probably the one we'll use. But I'm going to leave that wide open. I'll let you use any graph representation you think suits your fancy, and I'll see you online.